So if you remember, yesterday we had solved two problems on bolted connections, two example problems. The first one was of 6 bolts. This was the first problem that we had solved yesterday, where in the, let me check if you can hear me. Can somebody respond saying, yes, sir. Yeah, okay. So in the first problem, there were 6 bolts and there was a set of loads, basically a load was acting, that was 250 kilonewton, which was acting at an angle. So the good thing about that load was that that load was passing through the centroid of the 6 bolts, correct? So if you imagine that the centroid of these 6 bolts is somewhere here, so this is the location where the load was passing through. And as a result, there was no net moment applied. All the loads, and you can assume that the stiffness of the plate and this T section is high enough so that it does not lead to any uneven distribution of stresses. And as a result, all the 6 bolts could be assumed to be carrying exactly the same amount of force. And since it is passing through the centroid, since this load is not exactly aligned with the direction of the bolt, so the load is not perpendicular to the direction of the bolt, nor it is exactly parallel to the direction of the bolts. The bolts are in this direction, or in this diagram, bolts are in out of the plane direction. Okay, and the load is not exactly aligned or is perpendicular. So if the load were perpendicular to the direction of the bolts, then it would have meant shear forces for the bolts. If it was exactly parallel to the direction of the bolts, then it would have become tension force. But since it is neither, it is in between the two, this will have a combination of shear and tension force in each bolt. And that's what we observed, and we went through the exercise and we designed the bolt. I had made that mistake, which I have corrected in my slides now. I will pass it on to you. I'll upload this revised slide later. The second example that we had done was actually for a truss joint. So this could be a common truss joint. So a typical truss joint looks like this, wherein you have 4 members meeting at one place. These 2 members are aligned with each other. This member and this member. These are aligned. Okay, they are oriented in the same direction, and these 2 members are in different directions. And we checked that the force balance was satisfied. And then we were required to design the number of bolts. So as it was mentioned that this gusset plate also helps with the splicing. You understand what splicing means? Splicing means when one member becomes discontinuous and you carry on with some kind of a joint so that you can put another member after it. Okay, so splicing is often required in structures for various reasons. One, you don't always have large enough members, so you may require a truss of, let's say, 15-meter length. Okay, but there is no hot rolled section that is available which will provide you 15-meter length member. Even if it is available in the mill, it will be impossible to transport it to your site. Okay, so somewhere it has to be cut to a smaller size so that it can fit a truck or whatever transportation means you are using. Okay, so the members come in all these elements members come in a fixed size, right? So a limited size. They are not infinitely long. So when you need them, when you put them in structural in different types of structures, you have to do some kind of splicing. Splicing means you have to transfer load from one element to another element, both of them acting in continuation. Okay, so the member has a discontinuity. That is what splicing means. And therefore, this joint is also used as the location of splicing. And as a result, you have to design both members for the respective force demands. If that was not the case, if the member were continuous, you could have managed with the net force. Then you had to provide, later on we found out that each bolt had the capacity of 51.5 kilonewton. Remember? So each bolt net strength of the bolt was calculated as 51.5 kilonewton. So if this member was continuous, then we needed to provide the number of bolts that would suffice, that would support the balance force. So the balance force between this and this is only 200 kilonewton. So only 4 bolts would have been sufficient. Instead of 4 bolts, because we are also using this location as splicing, we had to provide 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bolts instead of 4, which is okay. Okay, we have not discussed the design of gusset plates. If you want to get into that, there is a lot of even most of the regular undergraduate, even graduate level textbooks don't talk about the design of the gusset plate. There is never enough time in a regular steel design course to talk about the design of gusset plates. Some of the limit states for gusset plates are similar to the limit states of regular tensile members, such as block shear failure and so on. But there may be some other considerations that have to be regarded. Okay, so then also we checked the block shear failure of each member as well? We have to check, but I had shown an example where only for one member it was checked, and we had found that this member, for one member we had checked, and for this member we found that it was safe in block shear. Okay. Likewise, one needs to check each and every member. All right. So now we will get into the third example. In the third example, there are a couple of changes from before. First of all the bolts are in shear. Now, there is no tension involved. The reason for that is that the force direction is perpendicular to the bolts, right? So bolts are in out of the plane direction here, and the force is acting perpendicular in the plane that is perpendicular to that, the direction of the bolts. Okay, so let me first explain the problem to you. You can imagine that this is a column flange. Okay, so there is actually a column and there is a flange here. Now, if you think of a flange, then there may be issue of a web here. So you don't think of an I section, you can think of a box section or something. So it's a hypothetical example classroom problem. So anyway, so you have got one plate, or for example, for this example, you can just think of this being a plate, simple plate. Okay, and then there is another plate which is basically a supporting plate, and pre-tension bolts are used. These 5 pre-tension bolts are used to tie the two plates together, join the two plates together, and a force demand is given here. So that force is acting at a certain distance from the centroid. So the distance is 400 millimeter at this location. Okay, that is 400 horizontal distance, and from the centroid, that point is 100 millimeter vertically away. Okay, and the force is acting at 60-degree angle from horizontal. Some other details are given. Grade M20 grade 8.8 bolts are used. Of course, you are going for pre-tension bolts, friction grip kind of a connection. In that case, you have to go for high strength bolts. So it has to be more than 8.8 or higher grades bolts. FU for such bolts is 800 MPa and FY is 640 MPa. Okay, that is basically not really yield strength; it's more like a proof stress. Okay, and the steel is still 410 grade steel, Fe 410. So your yield strength for steel is 250 MPa, and ultimate stress for steel is for the steel plates, both this plate as well as this plate, they are Fe 410 grade steel. All the plates are given as 10 mm thick plates. Okay, and the surfaces are sandblasted. So for sandblasted for surfaces, we had a mu value somewhere around 0.48 or 0.5, something like that. There was a table in the IS 800, which I had talked about. Okay, so now if you can imagine, the force is acting in the plane that is perpendicular to the direction of the bolts. So the bolts are in the plane perpendicular to the sheet, but this screen, but the load is in the plane of the screen. That is automatically making the force perpendicular to the bolts. Okay, and that automatically means that the force will introduce only shear forces in each bolt. Okay, none of the components of the force are parallel to the bolts. You understand that? So there won't be any tension. Okay, so it's only shear. Good. So second thing is that the bolts are configured in such a fashion: 1, 2, 3, 4, 5. The spacings are given in horizontal and vertical directions. The load, the net resultant load, is not really passing through the centroid. It is at an eccentricity. There is some eccentricity. The distance between this and the line that is corresponding to the load. Okay. So if you extend the line that corresponds that denotes this vector, if you extend this line, you can see how much eccentricity is there. And as a result of eccentricity, what will happen is that the force in each bolt will not be equal. Certain bolts will be carrying more force and certain bolts will be carrying less force. Now, how do we resolve this? Okay, so there will be some steps along the way. First step has to be to calculate the force demand in each bolt. Okay, so one approach could be that, let's say, these are the 5 bolts, 1, 2, 3, 4, and 5. These are the 5 bolts, and this is the load acting here. What I can say is that let me translate this load temporarily to this location, as if this load is actually acting here. Okay. So what I can do is I can say that this load is nothing but equivalent to a similar load acting here plus a torque or a moment acting here. Correct? at an eccentricity. So there is an eccentricity corresponding to this load, and that eccentricity introduces a moment. Okay, and what we can do is we can calculate that eccentricity. This force multiplied by that eccentricity will give me the moment demand, and this force directly will give me the force demand, direct force demand. Okay, so I know that there are 5 bolts, and assuming that the plates are all stiff enough, which is the typical assumption we make, unless the bolts are really far apart from each other, then you can't make that assumption. So in this kind of a case, the bolts are not too far apart, so you can assume that the force transfer, so this part here and this part here, so this part corresponds to transfer of direct force. So whatever the P force is acting, I can assume that P by 5, P divided by 5, P divided by 5, P divided by 5, and P divided by 5. That's how these forces are distributed between the 5 bolts. These drawings may not be very clear because they got pixelated when we transferred them to PDF, sorry, to the PPT. But I hope you are able to read them. Yeah. Let me know if you are able to read them clearly. Okay. All right. And the other component will be a moment acting about the centroid. Okay. So, and basically, why the centroid? Because we are calculating the distance from the centroid. We could be calculating distance from anywhere, and then it will be the moment acting about that point. So this is the centroid, and we calculate the distance from the centroid. So we know this is the direction of the force, and we need to do some geometric manipulation to get the eccentricity. Once we know that eccentricity, we know how much is the moment acting. Then what happens is that if the moment is acting about this point, let's say, okay, the moment is acting about this point, then what will happen is that this bolt cannot offer any resistance to that moment, because if there is a rotation demand on this kind of a connection, this bolt will not offer any resistance against rotation. However, that rotation will translate into translation for the bolts that are far away from the centroid, and for these bolts it will translate into some kind of a translation demand, or in other words, shear force demand. So these bolts will offer some resistance. Okay, now if you imagine that the plate where the bolts are placed, both plates, they are significantly more rigid than the bolts. So if the plates are more rigid, the force offered by each bolt will have a correlation with the distance, its distance from the centroid. Can anybody tell me what will be the correlation? So a bolt that is farther from the centroid, in this particular case, however, you will see that all 4 bolts are at equal distance from the centroid. So all of them will be carrying the same amount of force to resist that moment. And this bolt will be carrying 0 force because this is sitting right at the center. So, but if let's say there were bolts which were away from the center in different magnitudes, then what will be the relationship between the force share of each bolt versus the distance? Can somebody unmute themselves and answer?
So more the distance, lesser will be the force.
What's your name? First tell your name also.
So Omkar.
Omkar. More the distance, larger will be the?
No, lesser will be the force.
Oh, more the distance, less force. Why?
So because like is the again the centroid should be like at the center only. So means like if we take uh, like center of mass, means the more will be the distance. Like,
Okay. Anybody else? Nobody? At least try something, no? Even if you can't give the exact answer.
Sir, will you explain the question once again?
Okay.
Sir, actually, can you explain once again that why at the center the movement will like why the center bolt can't take that movement, will not take that movement?
Okay. First part you understood, right? So this force is, I'm transferring this force to the centroid. So if this force is transferred to the centroid, I can distribute that force to five parts. Each one will carry P by 5. That part is clear to everyone?
Yes, sir.
Okay. The second part is moment. So let's say these are the 5 bolts and I want to rotate the plate. Let's say there is this plate, this plate about this point. Okay, I want to rotate it. And let's say these 5 bolts were not there. And I just wanted to rotate this plate. Would the bolt have offered any resistance to that rotation? No, because the bolt would have acted as a hinge and the plate would have easily rotated around that point. It is only when you provide more than one bolt, then you start getting some resistance, because in that case, what happens is that for this single bolt, you can assume that the bolt is a point, just a point. Okay. So that will behave as a hinge, even though there will be local friction within the bolt. I understand that, but that local friction will be not enough to offer much resistance. What happens when you have bolts that are far away from each other, some finite distance away from each other? Then let's say I want to rotate about this point. Let's say I want to rotate about this point. Then for this point, it is not a rotation, it is a proper movement, a relative movement. Okay, relative translation. And that's when the bolt will start offering a finite amount of friction, finite amount of resistance.
But here it is pretension, no, sir. Why the center bolt won't resist the movement?
Um, I understand your question. See, the problem is that the bolt head is very small. If you imagine that the bolt head is so tiny that it will be very easy for me to be able to overcome, or for example, the bolt head is very small. So let's say there is a certain friction resistance it is offering. Now within the bolt head, at different distance away from the center of the bolt. So imagine that there is a center of the bolt and then there is a head perimeter. And at different locations, it is offering different amount of friction force. You understand?
Yes, sir.
Right? So, or let's say the friction is almost the same everywhere because friction coefficient is same. But then the point that is farther away from that center of the bolt, center line, if you imagine a center line of the bolt, the point that is farther away from that point will offer more moment, and the point that is exactly at the centroid will offer no moment for
Sir,
whatever the
we got
friction
that.
resistance it
Yes,
offers.
I got
Right?
that.
So now the thing is that entire bolt head is so small that the moment contribution coming from within the rotation, like within the bolt's rotation, is very small. However, if you have another bolt that is finite distance away, and that bolt is offering a certain resistance against translation, this
Yes, sir,
distance,
understood.
the distance between the two bolts multiplied by that force will be much more significant. So this resistance against torsion, so this resistance against rotation about this rotation about this bolt itself will be very insignificant. So you can ignore that. So we are ignoring that part. I didn't explain that. I assume that that was kind of very intuitive. So this part we are ignoring, any resistance against rotation. However, for other 4 bolts, it is a translation. The rotation of this plate, let's say, relative rotation of this plate with respect to this plate. So if this plate is rotating with respect to this plate about this point, then for all these 4 external bolts, it is actually a translation. Okay, and this is how the translation looks like. These arrows are a bit long, but you can imagine that if you see these are unit movements. So this is how this translation looks like. And what will happen for a bolt? Let's say this plate rotates by unit rotation, unit theta. So if the rotation is unit, then the relative movement of each bolt is proportional to what?
Distance from center.
Distance from the centroid, right? So there is a centroid here, which is obvious in this case. So this is the centroid, and the relative movement of each bolt will be proportional to its distance from the center. Okay, and let me. And because these are friction grip bolts, so because the friction will not be taken over, because that is the limit state. So friction cannot be taken over. So how is that relative movement taking place? That relative movement is taking place through the deformation of the bolt. Okay, so the friction is holding the uh, bolt head and nut with respect to the plate, and the bolt is deforming in shear to provide you this kind of a relative movement. Correct? So more the movement is, more force resistance it will offer until the friction takes over, until the friction is overcome. sorry, until the friction overcomes, till that time we are talking about. We are not talking about beyond the point when the friction has been overcome. So friction has not been overcome. Now the movement is proportional to the force. Agree? So two things we know now. The bolts that are farther away from the centroid will have more movement. Second thing we know, that the force is proportional to the movement. Correct? Because the bolt has to deform in shear to develop that, to allow that movement. Okay, so the force offer, the shear force resistance that it will offer will be proportional to the movement. Okay, another thing we know is that the moment contribution of that force is again proportional to the distance, because moment is force multiplied by the distance. So your force was already proportional to distance. The moment is proportional to force and the distance. That means moment is proportional to distance squared. So moment contribution of any bolt. So let's say we are rotating about this point. So moment contribution of each point here, each bolt here, is proportional to the distance square. Now you relate that with your torsional rigidity calculations. You are familiar with, or maybe moment of inertia calculations, moment of inertia, bending moment of inertia, A R square. Okay, so that basically means is that the contribution against bending, and similar thing holds true for a, let's say you have a circular cross section and you subject it to twisting, then any particle or any fiber that is r distance away, its contribution towards the stiffness of this, to overall torsional stiffness of the member, is r square proportional. Is that clear?
Yes.
Right? Okay, so that is just, keep that information in the background. In this particular case, all four bolts are equally distant from the centroid. So the moment contribution from each 5 bolts is going to be exactly the same. Yeah. So what I need to do is I need to calculate the total moment demand. Contribution from the bolt number 3 is 0, and the contribution from 1, 2, 4, and 5 will be equal. That is, so if I get total moment as m, then m divided by 4 will be the moment contribution from each bolt. Then what I can do is, once I know the moment contribution from each bolt, I know the force required in each bolt to contribute that much of moment. And that force and this force I can add with using vector calculus, not even calculus, vector algebra. Okay, so which are the steps? First, I need to calculate the eccentricity from the centroid, which I have done here. I don't want to repeat. This is a very simple geometry. You can go through this expressions here. This eccentricity turns out to be 296.4 millimeter. I think 8th or 9th grade students can do it. So I don't have to do it in the class, right? So eccentricity turns out to be 296 millimeter from the centroid. So this is that distance from here to the, so if I extend this line, so the distance from here to here is my eccentricity, and that I have calculated as 296. Okay, so once I know that, I know how much is the moment demand. Moment demand is PE, that is total force multiplied by E. For each bolt is going to contribute PE by 4, because only 4 bolts are resisting the moment, PE by 4. And since the distance is, so each moment is resisting PE by 4, and the moment is acting at this point, correct? The moment is acting at this point. So what I need to do is I need to calculate, in order to know the force, this force, I have to do that moment divided by the distance, correct? So that moment, PE by 4 divided by the distance, and that distance is, this distance is 50, and this distance is 50. The horizontal distance is 50 from the centroid, and the vertical distance is also 50 from the centroid. So 50 root 2, 50 multiplied by square root 2. That gives me 1.048 P in each bolt. Okay. So what it tells me is that here I am getting 0.2 P in each bolt, that is parallel to the direction of the force, external force, this external force. Sorry. And Then there is additional force in each bolt, and this force, so these forces, because of the direct force transfer or direct force, are all parallel, correct? Here they are all parallel, but these forces are not parallel. They are all going in the direction which is perpendicular to the longitudinal direction or the radial direction. So they are all going in the tangential direction, in other words. So this is the radial direction. What is it? This is the radial direction, and the forces are going in the tangential direction. Okay. So now what happens is that I have got this value as 1.048. Okay. Now, for some of these bolts, if you see, so for example, if I see bolt number 1, this P by 5 is acting for bolt number 1. This P by 5 is the external force. It is acting in this direction, or 0.2 P, or rather 60 degrees angle. No, so I will try to draw it at 60 degrees angle. 60 degrees angle from the horizontal. So 0.2 P here, and this force, this is also the external force. So I'm not drawing the resistance here. I'm drawing the external force that is acting on these bolts. The external force is in this direction, and this is 1.048 P. And as a result, the next external force are almost cancelling each other. Correct? Not completely, but basically they are acting in almost opposite direction. So the net force, if you calculate the resultant force, you will calculate, it will not be very high, because 0.2 P is negating 1.048 P. However, there could be some other bolts. Say, for example, look at bolt number 5. Bolt number 5. In this case, the two forces are almost parallel to each other. This is bolt number 5. This is bolt number 1. In case of bolt number 5, you have got 0.2 P in this direction, but you have got 1.048 P exactly opposite to 1. So in this case, it was here. In this case, it will be 1.048 P. Okay. So this obviously, bolt number 5 is obviously the case where the two forces are almost parallel. So the resultant will be much higher. So resultant in bolt number 5 will be much higher than the resultant force on bolt number 1. So as a result, we know that maximum force demand, maximum total force demand is going to be highest for which bolt? Bolt number 5. Okay, so I was able to do this just by visually looking at these things. If you're not sure, you can calculate the resultant for each one of them and then check the values. But calculation of resultant basically will require you to do some square roots and squares and so on. So I like this kind of an approach where I can visually see and figure out. Otherwise, you can just calculate the resultants.
So,
Yeah.
sir, you told that P is acting into the plane, right? Means, or means pulling.
Can you repeat? Can you repeat?
The force P is like acting into the plane, right?
In the plane, yeah, in the plane of this screen, yes.
Sir, then the forces at point one that which are shown tangential forces, like
Hmm.
where you have written 1.048 P, that
Yes.
force will be perpendicular to this P, right? Like P by
No,
5.
no. Why perpendicular to the screen? These are all. See, I had total force acting this much. That was P here. So what I have done is that this P is equivalent to a P acting here and a moment that is equal to this E distance, PE moment. Okay, so now I can get rid of my P, and this is the real state. This is the real final state. Okay, and these are how the 4 bolts are placed. So what I've got is I've got a force P and I've got a moment PE. Now this moment PE will be equivalent of this moment PE will be equivalent of these 4 forces. That's what I have calculated. So these 4 forces, which is each one of them is PE divided by 4, that is moment contribution from each one of them, and divided by 50 root 2, that was the distance. So let's say this is the force from each bolt that is in the plane of the screen. Okay, that's why it is a shear force for the bolts. If it was in out of the plane of the screen, that would have meant tension for the bolts, but it is not tension force for the bolts.
Sir,
So
this
this
P,
is, yeah. Tell me, sorry, I lost you. Hello.
yes,
Yeah,
sir.
who is this? First tell me your name also.
Omkar.
Omkar, tell me.
Sir, in that diagram, the
Yeah.
force PE upon 4 into 50 root 2 is like in plane force, right? That force is in
Yes.
the plane.
Yes.
Uh, and the force P besides the diagram acting at the center, it is
Yeah.
out of the plane, right?
No, no, no. All of them are in plane.
Okay, sir.
Yeah. Because see, the initially when this original P force was acting, this original P force that itself is in plane. And all I have done is I have moved the force, not exactly moved, but I have done this transformation wherein in plane itself, but I have imagined that this force, instead of acting here, is acting here in the same plane, and also it is contributing towards a moment which is m, which is equal to P times E. Okay, they are all in the
Yes.
same plane.
Yes.
Yeah, or in other words, what you can do is, all you have to do is, let's say this is, I'm saying this is the force in each bolt. You take this force, okay, multiplied by 50 root 2 will give you the moment about this point because of this force. Okay, that moment you multiply it by 4 because all 4 of them are contributing the same. Basically, you will get PE again. So basically, what I'm saying is that that force is equivalent of these. That moment, external moment, is equivalent to these 4 forces. These 4 forces. Okay. All right. I'm moving forward now. So basically, I've visually I have seen that bolt number 5 is going to have the highest resultant force. If you are not confident, you can do the calculation for each bolt and check out. Yeah. So what I know about each force is that this P by 5 was the direct force, and 1.048 P was the force demand because of the moment effect, the eccentricity effect. Okay, and this P by 5 should be acting at 60 degrees angle from the horizontal, that is 30 degrees angle from the vertical. They are same. And 1.048 P is acting in the tangential direction, and the tangential direction, if you can see, this tangential direction. So this is at 45 degrees from the horizontal. So I know these two things. So this is 45 degrees. So this angle is 45 degrees, and this is where it is acting. So now all I have to do is I have to take the horizontal component of this force and horizontal component of this force, add them together, square of that, and vertical component of this force and vertical component of this force, add them together, squared. Again, add them together and take the square root. Okay, so that's what I'm doing here. This is P by 5's horizontal component, that is P by 5 by 2, and 1.048 P is horizontal component. So both horizontal components I have taken, squared, plus, ignore this another plus, this is by mistake, plus vertical component of P by 5, that is P divided by 5 multiplied by root 3 by 2, that is vertical component. Yeah, plus 1.048 divided by square root 2, that is the vertical component of this force. Again added, squared, and square root of the whole thing, that gives me 1.242 P. Okay. So what it means is that for this whole arrangement, when I apply P force here, I get maximum force demand equal to 1.24 P. 248, right? 248, 242. 1.24 P I get, that is in bolt number 5. All other bolts will be carrying less force than this. So all I have to make sure is my bolt 5 remains safe. Okay. And this is a slip critical joint. So the bolt head should not slip against the plate, or the nut should not slip against the plate. That is the requirement. Or the plates should not slip against each other, both of them, right? And as a result, this as long as my bolt does not exceed that much of sorry, that is the force demand 1.24 P, and the bolt should be able to resist this much of force in shear. So I know what is the shear capacity of a slip critical joint. For the slip resistance of the bolt, the friction coefficient is given as 0.48 for a sandblasted furnace, the sandblasted surface as per the IS 800. So the nominal capacity in shear will be equal to the friction coefficient, and how many surfaces are in friction. It's only one surface. It's a single shear problem, one surface, and this is a clearance hole. The hole is not bigger than the minimum required, so therefore I'm taking 1. Then it is the proof load value. So that is the tensile, the pre-tension force, that is proof load. So that is 70%, 70% of, this is the net cross section area multiplied by FU. Okay, so that is the proof load. And from there I get the nominal capacity as 65.81. So the design capacity is under service load conditions. So I think it was mentioned somewhere that it was for service load conditions. At service load conditions for slip critical joints. So it is for service load conditions. So the factor of safety for service load conditions for slip critical joints was 1.1. It was 1.25 for ultimate conditions. So that is divided by 1.1. So I get a design capacity of 59.89 kilonewton. So basically 59.89 divided by 1.24, that is 1.24 P is the force carried by this force, which basically means that maximum P value that it can take is 42.4. Okay, so up to 42.4 kilonewton force is allowed on this joint. So P maximum value can be 42.4 kilonewton. Okay. Now you should be prepared for the exam to handle a problem where the bolts are not equally spaced. Okay, I'm just giving you a hint. So if the bolts are not equally spaced from the centroid, you should be able to handle that kind of a problem. Okay, any questions? No questions, huh? Good. Okay, so I think I can move to the next chapter now. By the way, I have not in bolted connections, there are various types of the bolted connections that I have talked about in, or even the examples that I have solved are relatively simplistic. These are not with all the details that are usually done in real life. So most of the real life bolted connections, in fact, nowadays fully bolted connections are relatively uncommon. They are done in trusses, they are done sometimes in especially towers, they are done. But even there, some part of the connection is still welded. So welded connections are quite common. I have not given you all the details. I have not described what kind of various connections are available. I'm hopeful that after I'm done with welded connections, because most of the real life connections are usually have some kind of a composite thing. So you have part weld, part bolted, and something like that. So I hope that there will be some time available after I'm done discussing welded connections where we can discuss real connections rather than these class textbook examples. Okay, but it is very important to first understand the textbook examples so that you know how the forces will be distributed. Then you get into the real actual connections. Okay. All right. So can I move forward to welded connections now? So in today's class on welded connections, we will just discuss some very preliminary things. There are various types of weldings that are prevalent. One is commonly known as arc welding, which is done through electricity. Have you guys, you have taken a course in workshop, right? You guys used to go to workshop wearing that khaki uniform, right? All of you have done that, right? That course? No? Anybody?
Yes, sir.
Yes, sir.
Yeah, you have done that, right? So have you had a practice with welding? Have you done any welding ever?
Yes, sir. Arc welding.
Arc welding you have done. Okay. Yeah, even we had done, I think in our BTech, maybe for, I think that was only one day where we had done, and I was terrible at that. I mean, I was, every time I would just bring the, I was not able to see through that shield basically. So whatever it is called, the welding shield or welding glass or whatever. So I couldn't see it, and I would touch the electrode with the base metal, and then suddenly it, the circuit breaker would go. So then they would say, bring it close and not touch it, but, or even if after you touch it, you have to remove it quickly. I was never good at it, so that guy got tired of me. He said, "Okay, I'll do it for you." So that is arc welding, and arc welding is of two primary types. One is MIG, another one is TIG. I'm not talking about those in much detail here. The difference between MIG and TIG is tungsten inert gas, and believe me, I just memorized these terms for this class. I tend to forget them. TIG is tungsten inert gas kind of welding, and MIG, and there are various synonyms for these terms. So you may hear say different word somewhere, different phrase somewhere. The person may be meaning one of the two. And the MIG is metal inert gas. Okay, the the most common one that you see every day is basically metal inert gas. So the metal inert gas basically has an electrode which is required in tungsten inert gas welding as well. But in case of metal inert gas, which is MIG, your electrode also works as filler material. Okay, so basically what happens in the process of welding, your electrode which you are holding, this thin rod which you are holding, and which is passing the current and creating the arc, that electrode is also the filler material. So it melts in the process and then gets deposited on the base metal. So you have a base metal like here. You have a base metal like here, and this is your electrode. And in the process, the electrode is melting and getting deposited on the base metal, and you are calling it weld metal here. Okay, the same thing is core wire. So before it gets more, it melts, it is core wire. After it melts, it deposits as weld metal. Okay. In case of a TIG, tungsten inert gas, you use tungsten as the electrode, and tungsten doesn't melt. As a result, you don't deposit any external material to the plates, to the base metal. As a consequence, you are expecting the base metal itself to melt and join. Okay. So these are the two types of arc welding. Then there is also stud welding. So stud welding is also in a way somewhat similar to your TIG, but you don't even need a tungsten electrode. Basically, when you weld the shear studs, you remember that I talked about shear stud welding a little bit, but didn't give you much description. You can of course go to YouTube and find hundreds of videos of how each of these weldings work. Okay, so in case of a um, this kind of a welding, basically again you don't deposit any external material as a that fuses the two metals. It basically counts on melting the base metals themselves. So your shear stud melts with the along with the first the deck, steel deck, and then the flange of the beam, and then the three of them fuse together. Okay, so that is the shear stud welding, this one. Okay. Um, for the arc welding, you need power supply, of course, you need electrode, right? And you need shielding atmosphere, which is flux. The use of shielding atmosphere or whatever that flux material is, that it oxidizes quickly and it creates some kind of an inert environment. Okay, so that because the molten metal is at a very high temperature, almost at a very high temperature, something like 2000 degrees centigrade or so. Okay, so at such a high temperature, these metals would very easily oxidize or react with the oxygen or nitrogen in the atmosphere. So the flux that you use here, which is basically which creates fumes, which are inert fumes. So these fumes don't react with the metal, and they create an environment where they push the oxygen and nitrogen of atmosphere away. So they push the atmospheric gases away and create this kind of a inert gases atmosphere right around that arc zone. Okay, and so the most hot parts of the metal don't oxidize, and because if they oxidize, then they are going to introduce lower strength and so on. Okay. Gas welding is also does not usually use a filler material. Sometimes you may use a filler material as well. That is your choice, but you can do gas welding even without using the filler material. And it is this same gas welding tool can be used, same kind of a flame, gas flame or gas torch can be used for cutting the metal. So often it is more frequently used to cut the metal than for welding. Okay, because mostly this gas comes at a high pressure and you have to be very careful, and the intensity has to be controlled so that you don't blow the molten metal away. Yeah. So anyway, that is done quite frequently, but most of the welding with this gas welding system is done for small works, not very heavy duty works. Okay. Now, within the arc welding, there are two common approaches that are taken. Okay. One is called submerged arc welding, and the other one is your regular welding. So next two slides are just two videos. The first one is just going to describe to you what typical welding looks like. Okay. So please let me know whether you are able to hear the audio of this video. Of course, you can see the screen, right? You can see the video, but whether you are able to hear the voice also. Were you able to hear the voice of this person? He was narrating something. Are you able to hear that?
No, sir.
No?
No,
No
sir.
or yes or
No,
no?
sir. No, sir.
No. Oh, you're not able to hear him. Let me see. I used to have that option somewhere where I can switch on this internal sounds of this thing also as it settings, turn on caption, change cloud. Okay, let me try to remove the So my mic was off. So were you able to watch the video? Okay. So there are a couple of things you should know. What the flux does, what is the purpose of the filler material, and what is slag, because there is a deposit of slag also that has to be chipped off later on. So after the welding is done, you have to grind the weld or you have to chip off the slag. You have to knock it with something so that that brittle surface forms on the surface that has to be removed. Okay. And that slag basically is all the impurities that come to the surface. Okay. Now this is the regular type of welding. You must have seen this kind of welding 100 times in your lives. This is another type of welding. Again, I'll click on this link and I'll share the video with you again. It's another video. Please watch it.
Howdy, y'all. It's Jordan Smith. We're still.
This is another video. Please watch it as well. This is only 4 minutes.
Out here in Houston, we are still at Arc Specialties, and today we are talking about sub-arc welding. What is sub-arc welding? It's submerged arc welding. It's been around since the 30s. It's one of the most efficient processes for turning electricity and wire into a weldment. You can get up to 100 pounds per hour with a multi-wire sub-arc process. With a single wire, you're putting down somewhere between 10 and 20, and then as you add the wires, you just keep adding the deposition. As long as you can travel fast enough and have enough amps to throw in it, this process will put down the material. It's used a lot in shipbuilding and anywhere else that you're joining large plates, having long runs, and you can mechanize the process. So pipe welding, those big electrical, what are they called? The electrical things, the poles, electrical poles. There you go, the big electrical poles that you see going across the country. Wind turbine generators, those big poles on there, all of that is welded with sub-arc welding. So what is sub-arc welding? Well, it's not underwater welding. Submerged arc welding doesn't mean that you're underwater welding. You are actually submerging your arc beneath the flux. So most people are familiar with a shielded metal arc or stick welding. You have your wire in the middle, and then you have your flux coating over that. When you weld, it turns into a slag that protects the molten metal. This works in a very similar process, but instead of having the flux coated over your wire, you put them in separately. So you have your wire coming off the spool, it runs through your contact tip. Most of the time you're running electrode positive, your workpiece is negative, and then your flux is actually in granules, and it comes through your flux nozzle, covers up both the welding arc as well as the molten puddle. Now when this flux is burned, when it heats up and melts, it turns into a slag, and that slag then coats the top of your weldment, just like it does on shielded metal arc. When you make this weld, the flux melts, turns into a slag over that, and then will pill up from the backside if you have everything set up right, and it will pill up, revealing the weld beneath. It's not a very visually interesting process, because if you do it right, there shouldn't be a whole lot going on. The things to remember when you're welding sub-arc is you want to make sure that you have the correct arc length underneath there that gives you a nice flat weld. It's not roped up and it's not too concave. You want to make sure you have the right flux burden. Too much flux and you actually won't let the gases escape, and you'll get worm tracks over the top, or worst case you get some porosity. And you don't want to see, you've got people that do it and they heavy and cumbersome. A ton of them. I know we've been post-action. I hope you want to see.
Okay, guys. So I think you were able to understand the difference between the two. The fundamental difference between the two things is that the first one is usually used by manually, right? And the second one is usually used in a mechanized manner. And the difference, another difference is that in the first one, the flux is coated on the electrode and it melts along with the electrode. In the second case, the flux is coming separately and it gets deposited. And another challenge with the with the second approach is that it's very hard to do that on an inclined surface. So if the surface has some inclination, that flux that you're depositing that is coming from a separate nozzle will not stay there. It will flow away. It will slide away. Okay, so such kind of situations you have to go with the manual kind of an operation. All right, but many of the large-scale works are these days done with submerged arc welding. Now, be very careful. Submerged does not mean that you are submerged in water. Submerged means it is the weld is submerged inside the flux. That's all. Okay, so that is more automized process. All right. So we will stop today's class here. We will continue with welded joints in the next class. If you have any questions, please send me an email. I'll try to answer them as soon as I can. All right. Thank you, folks. Thank you.